Hi, my name is Michael Cragness, and today we'll be discussing how to qualify sustainable packaging materials and also the nuances that are associated with these novel structures. I would like to say thank you to the TAPPI conference for allowing me to speak on this platform. And let's get right into it. We have a lot of information to cover. So why is permeation important? As we look at this picture here, it's a flexible pouch, right? But if we take a closer look, we see that it's standing up, meaning that it has a gusset on the bottom. It also has seams and it has a closure. Now, when I look at a package, I like to look at the package as a system consisting of different components. So all of these components, from the interface of the closure to the pouch, to the seams, to the gusset, they all have to be working properly, because they could all be potential permeation leak points. So now, of course, you're going to get water vapor and oxygen in the atmosphere. But say this is a flavored drink. So you may get some flavor loss in a process known as scalping, to where that flavor compound actually can be absorbed within the polymer that was used to seal the seams, or to convert this base material into this pouch. So you always have a lot of things going on. So you have oxygen trying to get in, because there's more oxygen in the atmosphere than there is in the product. And since this is a liquid, you would have a high humidified environment inside of the pouch. And since that relative humidity inside of the pouch and the partial pressure of that moisture is higher than in the environment, you're going to get moisture wanting to leave the pouch. So there's always multiple things going on at the same time. And that's why we have to really verify that we're going to get the shelf life that we propose, because there are a lot of factors that can play a role. So now, what is permeation? So we see here we have a 2-liter bottle, and it's highly pressurized with carbon dioxide gas. And then on the outside in the atmosphere, we have 21% oxygen. Now, at first glance, you may be thinking, well, how can oxygen that's at 1 atm permeate into a bottle that's at 4 atm of CO2? And the reason why is because of partial pressure. Now, partial pressure is really the driving force of permeation. So a general rule of permeation is more of it will go to where there is less of it, because it always wants to reach an equilibrium. So if I have a higher partial pressure gradient of oxygen on the outside versus the inside, oxygen is going to want to go into that bottle. And the reason that can happen is because there's less oxygen gas in the bottle, whereas the bottle has a lot of pressurized CO2, and the CO2 content within the bottle is a lot more than the atmosphere. So you're going to get CO2 gas that will want to move out of that bottle, which of course would make the soda, lose its CO2 gas. It would get flat. So this is a good example of how permeation works, and to where, depending on what chemical species, you can have a lot going on, even though at first glance you may not think that it really makes sense. So now we have a diagram of a package wall. So this could be the wall of this 2-liter bottle here. So we have a lot of oxygen in the room and not so much in the product. So that gradient is going to want to go from a higher concentration to a lower concentration. As you can see by this diagram at the bottom here, we call this the driving force for permeation, and that's based off of the partial pressure gradient. So you go from a higher concentration to a lower. So you're always moving down in concentration. And then that brings us to the first law, or Fick's first law of permeation theory. And that says the flux And the flux is essentially the volume of a gas that's passing through some medium. In this case, it would be a packaged sidewall. The flux is really dependent upon the diffusion coefficient of that sidewall, whatever that sidewall is made out of. If that's PET, that would depend on the diffusion coefficient of PET multiplied by the rate of change of the concentration between one side of the sidewall to the other. So we're going to briefly discuss what permeation is and the factors that influence it. So we have the diffusion coefficient. And as you can see in the units, it's measuring some area over time. And what's interesting about diffusion is that it's based off of random molecular movements. So not only does things want to permeate up and down and left and right, it wants to go in every direction. And it's just going to go in whatever direction it can. So a good example of this is if you order a pizza. When you first bring the pizza in the room, you know, not everybody can smell the pizza, but over time, maybe give it a couple of minutes or so, you know, that smell will permeate throughout the room and everybody can then smell what is for lunch. Now, to talk a little bit more in depth about the diffusion coefficient, it's an innate material property. So for each type of polymer or each type of material, it will have its own diffusion coefficient that correlates to some chemical species. So in this example, that chemical species is oxygen. So we're testing a bottle at room air concentration, 20.9% oxygen, and at 100% oxygen, to where we bagged the bottles and we piped in 100% oxygen. So we're going to challenge those with 100% oxygen. And then the test comes to equilibrium. And you can see the difference in the transmission rates. So that makes sense because 100 divided by 20.9 is about 4.8. So the difference in the transmission rate should be about 4.8 or so, being consistent with the concentration that we're challenging the bottle with. But what's interesting about the diffusion coefficient is, do you think that it took more time or less time for the 100% oxygen test to come to equilibrium versus the 20.9% oxygen test? The answer is it takes the same amount of time. Now, the reason this is because it's an innate material property. The diffusivity, it's measuring how fast some chemical species is able to permeate through some solid or some medium, rather. In this case, that would be this PET bottle or some type of coated bottle maybe. So now let's talk a little bit about solubility. Now, solubility, it provides a relationship between the partial pressure of the gas that's in the environment and also the concentration that's within that solid or whatever medium you have. So a good analogy for solubility is a sponge, because a sponge, it soaks things up. Whereas if you have a bottle or a flexible pouch, you know, what materials that those are made out of, they have a certain solubility at a certain temperature and relative humidity, depending on what chemical species we want to monitor. So a good example to discuss this would be if you have a piece of paper. Say you have a 1 inch by 1 inch square of paper, and you place that 1 inch by 1 inch square of paper within a humidified environment. Now you put it in at 23°C and 50% relative humidity, and you let it saturate that paper at those conditions, and then you take your final weights. So the moisture over time is going to solubilize within the structure of that paper until no more can be held within that structure. So we get one value at 50% relative humidity. Then we do this test again at 100% relative humidity. Now, the solubility factor, since it's at the same temperature, same type of paper, you'll get double the solubility or double the weight at 100% relative humidity as you would at 50% relative humidity. And that's because the solubility is actually, it's based upon and it's heavily influenced by the concentration. You know, one case is 50, one case is 100%. Just to speak a little bit further about permeation testing and flux and transmission rate. In the industry, transmission rate and permeation rate can be used interchangeably a lot, but they really are different. Fick's first law here, this is really has to do with the transmission rate of a material, which is basically you're measuring the flux coming through some film or some sidewall of a package. So you have your diffusion coefficient for that material, and then you have the concentration gradient or the rate of change of the concentration over some distance. Now this distance could be the thickness of a film or a package sidewall. So in this case, you're just measuring the volume of gas that's coming through some structure. To go a step further, we know that permeation is the product of the diffusion coefficient and the solubility coefficient. And what this ends up to be is that if you look at this last equation that actually is what is permeation, you have the quantity of some permeant, and then you have that normalized to the thickness over some area per some amount of time per some pressure drop. Now that pressure drop is across the membrane that the species is permeating across. So you see, if you're talking about permeation, you have to take into account the thickness of the medium that you're permeating. So that's the main difference between the permeation and a flux, is that you normalize for the thickness of the medium. So if you were looking at different barrier structures and you're looking in some book or some literature, it will always have the permeation rate because that gives you the best apples to apples comparison between a barrier because it's normalized usually to a 1 mil thickness or a 1 centimeter thickness. So it gives you a good gauge of what is a better barrier. So now, what's the process if we want to design something? As you see this graph here, there's a bunch of very well-known commodity type of packaging materials, the water vapor rate versus the transmission rate of oxygen. You have polyethylene is very high transmitter for oxygen, and it's an okay moisture barrier. And then you have steel or aluminum or glass, which is basically very low or essentially zero for moisture and oxygen. Now, when you're coming up with new sustainable materials, a graph like this really doesn't do you much good because you're creating a novel material that maybe you have a coated paper to where you have a paper substrate and some type of coating on that substrate. Or maybe you have a multi-layered structure that, you know, each layer may provide some different level of protection for your product. So when we're going to design more packaging materials, we have to ensure that we are testing those to be sure that we are reaching the barrier properties that we need to have the same shelf life as our traditional polymer materials. What are some ways that people meet these sustainable goals? Now, sustainability, it's not just about moving to paper or having a coated paper or somehow impregnating the paper matrix with some type of barrier. It can be something as simple as just having less plastic. Like for instance, of a drinking bottle, say you have a PET water bottle. One way you can make that more sustainable is just to use less plastic. So you just use a lightweight model where you make the thinner sidewalls. So you're using less material, easier to recyclable, and it saves you money on transportation. You could also use a barrier coating, you know, like some aluminum deposition, thin film coatings, nanocomposites. These are all used for different ways to provide a barrier to a substrate that is not that good of a barrier. And you also have bio-based and compostable packaging materials things that are called green polymers, something like PLA or polyvinyl acetate. Or you could even have things like post-consumer recyclable plastics, PCR plastics, to where it's been found that if you recycle certain plastics and use those recycled plastics as your resin to blow new bottles, it actually has some type of oxygen barrier component associated with a recycled resin. Now let's move on to paper. This is the broad subject of this presentation, because paper, as you can see by these photos, it really has a lot of porosity. And from that porosity, the structure contains a lot of extra surface area. So you can't just use wood or use paper as a barrier because it's porous, right? So you have to coat it somehow to make it a barrier. So looking at this example here, it's a paper substrate with the barrier coating. And we see on one side, we're challenging this sample here with a test gas. Let's say it's moisture. And then that moisture is going to move into the paper substrate, and then it's going to come or permeate through the barrier coating onto the other side to where we can quantify how much moisture actually permeated through this material. The thing with having paper as a substrate is you get this edge diffusion at the edges. Now the edge diffusion is essentially where the atmosphere can actually come in to the structure and can influence your driving force. So if you were at 100% oxygen on one side, it goes into the structure and you can lose some of that 100% oxygen out through the edges because diffusion is random. So the molecules want to move in every direction. So if it can move through the edges, it will. And it's also twofold because the atmosphere can also move in through the edges, which can also change your driving force. If you're running a water vapor test, if you have a very high humidified environment, that moisture can actually move into your structure and cause your water vapor transmission rate to increase because the edges were open or you did not seal the edges and the edge diffusion took place. So this is really what makes paper very hard to test accurately and repeatably. And it you have to really sometimes do trial and error and take different methods depending on the situation. So what are some common issues with testing paper? You could have it transmit just too high. You know, paper is not a good barrier, and if you put a coating on it, maybe the coating has a pinhole or the coating is not consistent. Maybe it has a rough surface. A lot of coated paper has a very rough surface, and rough surfaces, they do not seal too well in instruments because you need a smooth interface because we're dealing with gases. So if we have a gas on each side, we need to be sure that we're creating a hermetic seal between the two sides. You can have porosity issues, which is what I just spoke of in the slide before. You get the potential in the presence of high humidity, you get the potential for the substrate to swell because paper likes to swell in the presence of moisture. This could compromise your coating or crack your coating. Another method that you may use to test a paper-based material is that you may mask it. And what that will do is, as I'll show you here shortly, is that you can have a scenario where the effective area of your sample is contributing to your transmission rate, and it's not the same as your defined area. So the first thing we'll discuss is double foil masking. Now this is a good option because if our paper coated material is transmitting too much oxygen, we can actually mask it to a smaller area so the flux coming through that material is a lot less. So what this will do is this will increase the upper testing limit of our instrument. So in this example here, you have some masked samples, and then you have a full size 50 centimeter squared area sample, and you take the sample and you mask it, to set 10 centimeters squared. Now what that's going to do is that's going to increase the upper testing limit by 5 times because we're masking down 5 times. So for example, if you have a coated paper that's about 200 cc's per meter squared per day in transmission rate, and you have a full-size sample and the instrument can only go up to 100 cc's per meter squared, you're going to have an issue. It's going to overrange your instrument. But when you mask it, you're allowing that instrument to now have an upper limit of 500 cc's per meter squared per day. So then you would be able to get data on your material that's around 200 cc's per meter squared per day. Now, one thing to keep in mind is when you're double foil masking, which is essentially sandwiching your material in between 2 foil masks, and you have some well-defined test area, you have to be careful what area you actually mask, because this area should really be as consistent as possible and not have thin spots or other flaws within the area, because that's going to become magnified. That's going to heavily influence your results. So you'll want to find a piece of material that is very consistent, has a good robust coating on it, to where the coating, has a consistent uniform thickness. There's no flaws in the material, like a crack in the coating or maybe a pinhole. And that will give you your best chance at getting good repeatable data. So talking a little bit more about double foil masking, we have these diagrams here. So if you take a cross section of a double foil mask, what's going on? So in these example, we have oxygen, or H2O, on one side. So that's moving into the material. And then because it's paper, it's going to want to move all throughout the material because, it has porosity. So diffusion being random, it's going to want to move through the material and through the sides and basically anywhere it can go. So double foil masking can be a good option if you have a thin film. And since it's thin, it doesn't have much edge to it. So the adhesive from the foil masks, it can actually be sufficient to seal the edges of your thin paper. So when you double foil mask a thin paper, a lot of the times, if the adhesive sticks well to your sample, it will seal off those edges inside of the mask, so you won't get this edge diffusion. So then you can rest assured that all of your flux is actually going through the film and you're not losing driving force. But there's also something you must think about, because a lot of coated papers actually have a textured surface, or it's rough. So if you have a rough surface and you seal it within a mask, the mask, you're going to have voids, and those voids are actually going to leak. So then you'll get erroneous data because it's actually not fully sealed. So where if you look at the diagram on the right, the cross section shows in red, that's the epoxy. So you would want to apply epoxy to the perimeter interface of the mask and the actual sample, as it shows below. And with these photos here, I double foil masked a paper sample, and then since I epoxied it, I have to take the new area of it, because it's no longer 5 centimeters squared area like the mask is, because I added epoxy. So this is something that you would have to do if you were testing a paper-based structure that had a rough surface. This is one way that you could do it. So what's another solution we could try? So since we had already talked about edge diffusion, this example here it's pretty self-explanatory. We have a coated paper sample and we put it on one mask. And then what we're doing is we applied epoxy to the edges. We cover the edges with epoxy and bring the epoxy all the way to the defined test area. Now what this is going to do, it's going to make sure that we're not getting any edge diffusion, because the epoxy is going to act as a barrier. So it's going to force all of the flux to go through the material, and we're not going to lose any through the edges. Now this this works really well, and it's kind of the gold standard approach that we take to testing a lot of paper-based materials in our lab. But there are certain nuances involved with this. Like you have to be sure to get it within the O-ring that actually seals that side, because if you cut your sample too large and then epoxy the edges, and the O-ring is actually on top of the epoxy, when you seal the instrument, it's going to crack the epoxy, and then you're going to get more leaks. But this is a very good visual as to what sealing the edges does to stop that edge diffusion, and it works very well for a lot of samples. But one thing you have to keep in mind of is how well does the epoxy stick to your material, because not all epoxy stick to all coatings, and this can cause an issue, because if the epoxy does not properly adhere to your sample, you can actually get a leak to where you can have molecules slowly come underneath the epoxy and actually move through underneath the epoxy and move to the other side and give you a false transmission rate. Another approach we could take is you look at this paper film in a test cell. You have your test gas challenge in one side, so let's say you have 100% oxygen. And then on the other side, you have your carrier gas. So whatever oxygen permeates through the film, that carrier gas is going to take it to the detector, so we can quantify how much oxygen is coming through the film. But here on the left hand, you see the light blue arrows. That's actually atmospheric oxygen that's coming into the structure from the atmosphere. What that's going to do is that's going to dilute our driving force. We're no longer going to have 100% oxygen. And another thing it can do is the 100% oxygen can actually leak out through the same edges. So you get this edge diffusion, and what it does is it gives you a questionable driving force, so you really don't understand what your challenge is to that material. So what we did was we came up with a cell that actually it blocks your edges, as this example on the right, to where it has like a dam over the edges of the paper sample, so you don't get any atmospheric influence. So it seals the edges physically by having basically like a fence around the perimeter of your material. And looking at these photos here, you see here this cell that has a raised lip. So that actually blocks the edges from having any edge diffusion. And this works very well. It works good for thicker materials and some thin materials, that have a good coating, either on one side or on both sides. But the sealing surface must be smooth, otherwise it's not going to seal properly. And as I said before, a lot of coated paper materials or paper-based structures actually do have some texture to them, so they would not seal properly in this cartridge here. So just to discuss a little bit about a case study that we did with this edge effect cartridge, we ran a water vapor test at 23°C and 50% relative humidity. So we ran the same test at 2 different times of the year. So we ran it with our standard cell that would have the edges left open to the atmosphere, and we ran it with our edge effect cell that's actually covering the edges. So in the winter time, we ran it, the room RH was only about 20%. So you see with the standard cell, that actually lowered the driving force because it was leaking in through the edges. So we got a lower transmission rate than we did with the edge effect cell. And then we did the same measurement in July when the relative humidity in the lab was a lot higher, so that you could see that actually influenced the results. So it made the water vapor transmission rate a lot higher. Whereas when we tested it with our edge effect cell, it was very consistent with the reading that we took in the winter time. So now another solution that we use to test these type of structures, where we actually compress the microporosity by using a force to essentially remove the porosity from the material. So you see in this diagram, we have a porous piece of paper, and then we have raised lips on both sides. And these raised lips, they bite into the structure, and we have a compressive force that actually compresses the perimeter of the sample. Now, what this does is it compresses it so much that it actually removes the microporosity, so it removes the edge diffusion. So it seals it off, so our atmosphere can no longer come into the structure. And these are some real pictures of the actual test cell. You see we have the raised lip parameter, and then we have our screws. So we would torque those screws to some specification, and that would cause enough force to actually compress the material so there's no edge diffusion. And if you look at the pictures on the top right, that's what a sample looks like after it's been compressed. You see that you can see a very clear area to where the compression took place. Now, this works really well for thin materials that are smooth, and thin materials that have some type of texture to them. Whereas this does not work the best for thicker materials, because when we torque the screws down, it actually may cut the material. As you see what happened in the bottom there, that picture, you can run into that issue if you use too much force, or if you are trying to compress like a cardboard or a much thicker paperboard. So a lot of our customers, they're getting into coated paper, and coated paper it's still a young industry. So this graph is actually showing real data that I ran from the same material. All three of these samples were cut from the same sheet of material. The first one, I got very low values. It was a good barrier. The second test, it was an okay barrier. And then the third test I ran, I got values that were much higher, much higher. And the reason this is because of the coating. How good was the coating? How consistent was the coating? Did the coating have pinholes? Did it have thin spots? These are things that you have to test for, and this is very typical. So that's why testing coated paper can be very challenging, because you can get very different repeatability, and then you may question, is it how I prep the sample? Is it my mask? Is it the coating? Is it the instrument? So you have to really, a lot of times, use trial and error and make observations and see which is the best method by doing tests. A lot of times that means you'll have to run multiple tests, maybe using different methods, and seeing which makes the most sense over time. Now, a lot of our customers always ask me, well, what should be the test parameters? What temperature and what RH should I test at? And I'll always say, well, the best tests are actually the ones that your material is going to experience and service. So what are the applications? How do you package your material? Like, wherever you make this material, what type of environment? Is it in a high humidified environment? How do you transport it? Do you fly it in with a jet, or do you put it in a semi-truck that has to drive across the country? Is it going to be very hot and humid in that semi-truck? Does a semi-truck sit for 2 or 3 days before it gets to its destination? What's the warehouse? What are the conditions in the warehouse? What are the conditions when it's being delivered? Like, does the package get moved a lot? Does it bounce around? Because all of these things can actually cause your coating, or cause more oxygen ingress or more moisture ingress into your package. So say, for instance, you made a pouch out of coated paper, and you have something like pistachios within there. So pistachios, they're pretty hard and they kind of scratch things. They're abrasive. If this is being shipped, and when they're shipping it, they're moving it a lot, or it's jostling around and bouncing up and down against the package, it can actually potentially scratch some of that coating. Just from the handling, from the shipping and handling, it can actually compromise your barrier. And then you may have to think about, okay, well, it's shipped on semi for 3 days in a very hot and humid environment before it gets to the store. But that hot and humid environment in the truck is a lot different than the temperature on the shelf. So doing your due diligence and understanding your supply chain will help you make the best decisions when you're verifying, does my new material stand up to the conditions that it's going to see in real life? And will it be good for my customer for the proposed shelf life? So how would you apply shelf life? So you've ran your tests, you've got your data, you know what the transmission rate is. So now what? How do we use that to determine what our shelf life could be, or if it meets our shelf life? So in this example here, your food scientists or your sensory panel people, they'll tell you, what is the total amount of oxygen that can come into this package and still meet your proposed shelf life. So in this example, for 180 days, you can only have 8 cc's of total oxygen. So then we take our transmission rate, we multiply that by 180 days, and we see that we're only at 6.8 cc's of total oxygen over that time. So then this coated paper pouch would actually be good for this product for 6 months. Now, this is just an example. This really is not reflective of the industry, the coffee industry. This is just for example purposes only, these numbers, just to show you how you could use the data in a practical method. And you would repeat the same process for nitrogen and for CO2 on this package, because nitrogen and CO2 are both important for roasted coffee beans as well. This package has different components. It has a resealable pouch interface. It has the easy open tear notches. It has your seams. So all these different components, they have now created potential leak regions to leak into our pouch. So we're taking this whole pouch after it's been converted, and we're doing a whole package test on this pouch. So we're gonna put it in an environment, and we're gonna have nitrogen gas flow on the inside volume of the pouch. So whatever moisture comes into the pouch, if that moisture comes in through the seams or through the easy tear notch opening, we're gonna measure this whole system. So then we know exactly what this system is going to do when it has to go through the supply chain. You will have to verify these new materials to ensure that you're going to have the same barrier as your old polymer material did. So you have to do enough testing so that you're confident that your new package will be able to withstand your supply chain and protect your product. And you also have to always test the whole package, because that's really the end game, and you're only as good as your weakest link in permeation. Because if you have a very good foil barrier and you turn it into a pouch, if the closure is not good, then the system is not good. Or if the induction seal is not good, then the system is not good. If one of the seams is leaking, then the whole system is not good. So we should always view packages as a system, and then we have to do our best to test the system to make sure that the system is actually giving us the barrier that we want for our product. And if it's not, then we can test it in different ways to figure out where the problem is, because we're only as strong as our weakest link. So thank you for your time today.